Good morning students. Today we will cover a new topic, that is expansion of size of a MUX. Now what is expansion of size of a MUX? That means suppose we want to implement a Boolean expression of 3 variables. So for a implementation of 3 variable Boolean expression, what is the size of the MUX we require? 8:1. Because if number of variable is 3, then what should be the number of input line of the MUX? 2 to the power of 3. Right? So 8 and the output is always 1. So 8:1 is the size of the MUX if we implement a 3 variable Boolean expression using a multiplexer. Now suppose we don't have an 8:1 MUX, but we need to implement a 3 variable expression. Then what can we do? Then we can do the expansion of MUX size. That means if we have two 4:1 multiplexer, instead of having a single 8:1 multiplexer, then we can use those two 4:1 multiplexer to make a 8:1 multiplexer. That is to implement, better to say, to implement a 8:1 multiplexer. So, a 8:1 multiplexer can be implemented by using two 4:1 multiplexer. Similarly, a 4:1 multiplexer can be implemented by using two 2:1 multiplexer. A 16:1 multiplexer can be implemented by using two 8:1 multiplexers. Right? So, our two half size multiplexer can be combined to implement a larger size multiplexer. That is called expansion of multiplexer. Now to do this, for expansion of multiplexer, we need to learn another input line of a multiplexer, that is preset line. PR. This is preset line of the multiplexer. Right? Now see, our multiplexer is having two type of input lines. One is the input lines. This is a 4:1 multiplexer. So there are 4 input lines and select lines. For a 4:1 multiplexer, there are 2 select lines and only 1 output line. In addition to this, the preset line is another input line, a different type of input line that is also used for a multiplexer. Now what is the utility of this preset line? Suppose if this preset line is directly connected like this, then this type of multiplexer can be called active high preset. Now what is active high preset? That is, if this preset line input is equal to 1, then the multiplexer is activated. This multiplexer is activated. So this multiplexer will operate according to the select line and input line inputs. Its normal operation. The multiplexer will do its normal operation. Now if this preset line input is equal to 0, then this multiplexer will be deactivated. Right? This is for active high preset. So deactivated means it will not perform its normal operation. The output will not give according to the inputs. So to activate a multiplexer, this preset line input is equal to 1 in case of active high preset. Now in case of active low preset, it is just opposite. Then preset line is connected through a bubble. This bubble is actually a NOT gate. Then this multiplexer will be activated when this preset line input is 0 and it is deactivated when this preset line input is 1. So this is the significance of preset line. Now this preset line, this will be used for expansion of size of a MUX. So let us see how. See, we will implement this Boolean expression by using expansion of MUX. That means, see, this is a 3 variable expression. How many input variables are there? 3. A, B, C. So, if we use a single multiplexer, then we require a 8:1 multiplexer, 2 to the power 3. Number of variables at 3. So, how many inputs will be there? 2 to the power of 3, that is 8. So, the size of the MUX in direct method of multiplexer designing will be 8:1. Now in this expansion method, we will implement the same Boolean expression by using two 4:1 MUX instead of using a single 8:1 MUX. Okay. Now this is our truth table. See, truth table, how we have derived this? There are 3 input variables A, B, C. So, these are the 3 inputs. So, how many input combinations will be there? 8 input combinations from 0 to 7. So, 0, 0, 0 to 1, 1, 1. Right? This is combination 0. This is 7. 0, 1, 2, 3, 4, 5, 6, 7. Right? Now, in this min-term expression, which of the numbers are mentioned? This is a min-term expression. So, small m must be written. So, which are the numbers mentioned over there? 0, 1, 3, 5, 7. Right? So, for those input combinations 0, 1, 3, 5, 7, the output must be 1. See, for 0 it is 1, for 1 it is 1, for 2 it is 0 because 2 is not mentioned, for 3 it is 1, for 4 it is 0 because 4 is not mentioned, for 5 it is 1, for 6 it is 0 because 6 is not mentioned, again 7 is mentioned, so for 7 it is 1. Right? So, this is our truth table. Now, we will implement this truth table by using 2 4:1 MUX. See, this is the design. See, we have used 2 4:1 MUX. Right? This is MUX 1, this is MUX 2. See, we have used the preset lines for this expansion purpose. Now, how the preset line is used? See, the upper one, the upper multiplexer is active low preset. That means this multiplexer will be activated only when the preset input is equal to 0. Right? And the lower multiplexer, this is active high preset. This is active low preset. So, this multiplexer will be activated when this preset line input is 0, and this is active high preset, this multiplexer. So, this multiplexer will be activated when this preset line input is 1. Right? Now, see, so both of these multiplexer will not be activated simultaneously, isn't it? Because this preset line, this is a common line, common input line for both the MUX. Right? So, it may be either 0 or 1. It is a common input line. So, you can supply either 0 or 1 to this input line. So, if this A is equal to 0, suppose, then this MUX will be activated, this will be deactivated. If A is equal to 1, then this MUX will be activated and this one will be deactivated. Okay. So, both of them will not be activated simultaneously at the same time. One after one, the activation will be there. Now, see how we have connected this A. See, there are 3 variables A, B, C. We have connected the MSB variable A at the common preset line input. And other 2 variables B and C are given to the common select line for both the MUX. This is the select line for both the MUX. This is S1, S0, select line for this MUX. Again S1, S0 for this MUX, select line for this MUX. So, B and C are the common select line for both the multiplexers. Okay. Now, let us see how the inputs are connected. See, this MUX is having 4 inputs as this is a 4:1 MUX. Again, this MUX is having 4 inputs as this is a 4:1 MUX. Now, the original multiplexer, that must be 8 inputs. If we would have used direct method, right? So, 8 inputs must be there, I0 to I7. See, this I0, I1, I2, I3, and this I0, I1, I2, I3. This is same. That means this 4 input of the higher MUX is used as the original 4 inputs, I0, I1, I2, I3. And rest 4 inputs are actually used for I0, I1, I2, I3 for this second MUX. So, this is I4, I5, I6, I7. Right? That means actually if it was a 8:1, then how many lines would be there? 8. Right? From I0 to I7. This I0, I1, the first four I0, I1, I2, I3 we have given to this marks, and the next four I4, I5, I6, I7 we have given to this particular marks. Okay. Now see how it is working. Let us see how it is working. First see for the first combination 0, 0, 0. So if this designing is, again another thing is there, both the outputs of the multiplexers Y1 and Y2 are passed through a OR gate, and this is actually the ultimate output. This is the ultimate output. Now let us see how the multiplexer is working. This is actually, this whole is actually a 8:1 marks, which is comprising of two 4:1 marks. I0, I1, I2, I3, these are the inputs for this first marks, and the next four inputs of the of the 8:1 marks, that is I4, I5, I6, I7, those are given as the inputs for the second marks, that is I0, I1, I2, I3. Right? Now see what is happening. Now we have to cross check this truth table. If this truth table is verified, then we can say that our designing is okay, right? So let us see whether our truth table is verified or not. See for input 0, 0, 0, right? So A0, B0, C0. So if A equal to 0, then which marks will be activated? This one, this marks 1, right? Because this marks is active low preset. That means this A is given to the preset line. When this preset line input is 0, this marks will be activated, right? That means it will give its output according to the select line and input lines. And this marks is deactivated there, because this is activated when only when preset equal to 1. So for A equal to 0, this is activated and this is totally deactivated, right? So we will not consider this marks till A is equal to 0. That means till this point, right? For these four combinations, A is equal to 0. So for 0, 0, 0, what is your output? 1. See, for 0, 0, 0, B equal to 0, C equal to 0. So BC equal to 0. So S0, S1 for this marks are 0, 0. So which one input will be selected? I0. So Y1 is equal to I0. Now what should be connected to I0? So that we will get this output. See, Y equal to 1. So we will connect logic 1 to I0. Right? Now see the next combination 0, 0, 1. So BCR 0, 1. As BCR 0, 1, BCR 0, 1. So which one input will be selected? I1. So Y is equal to I1. Now what should be given to I1 so that we should get this desired output? See, Y is equal to 1. So we must connect logic 1. Now see the next combination 0, 1, 0. So BCR 1, 0. Right? B equal to 1, C equal to 0. So 1, 0 means 2. So which one input should be selected? I2. And Y is equal to I2. Now what should be connected to I2 to have this desired output? See, Y is equal to 0 for 0, 1, 0. So we must connect logic 0. Okay. Now see, the next one is 0, 1, 1. So BCR 1, 1. B equal to 1, C equal to 1. Right? So for 1, 1 combination, which input will be selected? 1, 1 means 3. So I3 will be selected and Y is equal to I3. Now what should be connected to this I3 line so that we must get 1, because for 0, 1, 1 the output is 1. Logic 1. Okay. Now see, the next combination is 1 0 0. See, now our A is equal to 1. So if A is equal to 1, this MUX will be deactivated and this one will be activated, because A equal to 1, that means preset line input is 1, the common preset line is 1. So when common preset line is 1, this will be activated because this is active high preset. Okay. So this MUX is now activated and this is deactivated. So for all these 4 combinations, A is equal to 1. So for all these 4 combinations, this MUX will be activated and this one will be deactivated. Simply. Right? Now let us check the input combinations. See, 1 0 0. So B is equal to 0, C is equal to 0. So which one will be selected? I0 for this MUX. Right? See, I0 for this MUX is actually I4 for the whole 8:1 MUX. Right? So because this is, if I0, this is I1, this is I2 combinations, I3, I4, I5, I6, I7. Actually we are splitting this whole 8 inputs into 2 MUX. Right? So see, for 1 0 0, S1 is 0, S0 is also 0. So I0 from this second MUX will be selected. Right? So what should be given at the input so that we get 0 at the output? Obviously logic 0. Right? I0 from this is selected. So Y2 is equal to I0. So I0 must be logic 0 to have the output 0. Now see, for the next combination 1 0 1. Right? So for 1 0 1, BC are 0 1. B is equal to 0, C is equal to 1. So for 0 1, which one is selected? I1. So what is your Y? Y is equal to I1. So what should be connected to I1 so that we get this output? We must connect logic 1 because this is 1. Right? Now see, for the next combination 1 1 0. 1 0. BC 1 0. For 1 0, which one should be selected? I2. Right? 1 0 means 2. So I2 is selected and Y is equal to I2. So what should be given to this I2 line? To have 0 output, logic 0. Right? Now the next one is 1 1 1. So BC are 1 1. So for BC 1 1, which one input will be selected? I3. Right? So Y is equal to I3. Now what should be given to I3 line to have this output, desired output 1? We must give 1. Right? So then only the output is 1. Now see, Y is accumulating all the outputs. So what are the outputs for all the combination from this first MUX? The outputs are 1 1 0 1 for the combinations of 0 0 0 0 0 1 0 1 0 0 1 1. Right? And the outputs for this are 0 1 0 1. 0 1 0 1 for the combinations of 1 0 0 1 0 1 1 1 0 and 1 1 1. Right? So at a time, for a combination, for any of the combination, at a time we are getting only one output, either from this MUX or from this MUX, and that particular output is passed through a NOT gate to have Y. So what will your Y give? Y is equal to the ultimate output that will combine all these outputs 1, 1, 0, 1, 0, 1, 0, 1. 1, 1, 0, 1 and 0, 1, 0, 1. Right? So, starting from 0, 0, 0 combination to 1, 1, 1 combinations, we will have these 8 outputs one after another. For 0, 0, 0 combination, we will have 1. For 0, 0, 1 combination, we will have 1. For 0, 1, 0 combination, we will have 0. For 0, 1, 1 combination, we will have 1. For 1, 0, 0 combination, we will have 0. For 1, 0, 1 combination, we will have 1. For 1, 1, 0 combination, we will have 0. And for 1, 1, 1 combination, we will have 1. Right? So this is all from this class. We have used two 4:1 multiplexers to design a 8:1 multiplexer. Actually, this is used when we don't have 8:1 multiplexer or a larger size multiplexer, but we need to implement an expression in direct method to of that size that requires that particular size of multiplexer. Suppose 8:1, but if we don't have 8:1, then we can use two 4:1s also to implement the expression that requires a 8:1 multiplexer, right? So this is called expansion of multiplexer. This is all from this class. Thank you for watching, and if you not yet subscribed the channel, please subscribe the channel to have the recent videos. Thank you so much.